hey, these problems at the end are really nightmares. So I actually did them, 5, 6, and 7 in full, but then you probably got my email saying, hey, those are nightmares. You don't have to do the whole thing. Uh, I was really most interested in just exploring this idea of a harvesting. And so the harvesting is this. So you have this normal logistic growth, and then you have a harvesting, which is how much you're going to take out of the population each year or each time period. And you want to make sure you don't take out so many that you completely destroy the population. So with number 5, here's what I did is I just said, okay, there it is. I can easily solve that, and I can get, although they kind of told you what the equilibria were, and so, but here, I'll just show you that I could do it. Here are the factors. P minus 4 and P minus 1, is it? Something like that. So anyway, you could do this yourselves. You get those two equilibria, and here's what the sort of the different solutions look like. You have an equilibrium at 1, an equilibrium at 4. Anything above 4 ends up leveling off at 4. By the way, the 4 is probably like 4 million fish or 4 trillion. I don't know how many, but it's probably not 4 fish. It's probably something like 4 million fish in the population. So if you have too many fish, they die off, and you end up leveling off here. If there are too few, or not too few, if they're between 1 and 4, you increase and level off at 4, and then below 1, that's when you're going to die off. The question B, part B, well, yeah, it was part B, wasn't it? Yeah, part B was asking for how long, or maybe it was part C, it doesn't matter. How long will it be until you die off? And so to do this, I actually, in the process of solving that part, I realized that that was actually easier than I realized it. And here's why. Let me just show you how you would solve this. So I didn't do it by hand. I actually just used Python, but I'll show you my Python in a sec. But here's what you would do is you would do this. P minus 4, P minus 1 is equal to negative dt. Integrate both sides, and you get negative t plus c is equal to whatever. And then from that, you could figure out c, because when t is equal to 0, you'd have whatever sub 0 is equal to c. But anyway, the point is that if I want to know when the population is 0, so if I want to know when it's going to be 0, here's when it's going to be 0. It's going to be time is equal to whatever, evaluated at 0 over, is it over or minus? Maybe it's minus. Yeah, you'll actually see this. I actually do it in Python. Minus whatever sub-0. Sub-0 is the original population, and then evaluated at 0 just means when the population equals 0. That's what I'm trying to express there. So you get something. It's going to have some natural logs, obviously, but it actually ended up, I realized in the process of doing it on Python that it really wasn't as complicated as I had, like I looked at it and I thought, no, it's going to be hard, but actually it turned out to not be so hard. Here, I'll show you my Python, and then we can play around with it. Where is my Python? There it is. Okay, yeah, so I've got my little cheat sheet here that I use every time I want to do calculus. It's called calculus. Okay, so where is it? There it is. There's the work that I did. So, so I've got a equals 5, b equals 1, h equals 4, and then I integrated. This is the whatever that I mentioned. I'll show it to you in a minute because I printed it. And then I solved this for t, and that's the whatever evaluated at 0 minus whatever, or the whatever it is, yeah. Anyway, and so I printed that just to show you what it looked like. And then in addition to that, I was curious, whoops, where is it? I was curious to see, like, what would happen, how long will the population survive if you start off with 0.5? So halfway between, like, how long, and then what if you started with 1, 1.5, 2, and 2.5? So I just printed, I could have made a loop, I realize, but whatever. So there it is. I just cut and pasted. So here's the whatever. This is the integral that I mentioned, the log of, that's the natural log actually. So natural log of p minus 3 over 3 plus natural log of p minus 1 over 3. And the first one is negative. Then the second one, this is the answer to the question C, is it? Like if your population is p0, if it starts off at p0, then this is how long the population will survive. And then I plugged in the different numbers. And for this particular one, if you start off with 0.5, you're going to last this much time. If you start off with 1, apparently you go to the zoo. No, actually, no, that's not that one. That's Python speak for the infinity in the complex plane. So the reason for that is because you never die out if you start off with 1. And here I'll show you why. So if you start off with 1, you're at an equilibrium. You never get down here. So it's just, well, how long is it going to take? Infinity. And then the other ones, if you're starting out above 1, it gives me some complex number, which once again, you're never dying out. You're actually getting bigger. So there's that. But the beauty of this, since I've got it all typed in here, is that I can adjust the amount of harvesting. So part number six, they asked you to harvest 25/4. Let me just show you on this first so you can see what it looks like. So here's number 6. So that's what, yeah, sorry, it's a little bit of a mess. Here's what you start off with. You're subtracting off 25/4. This thing factors. It's actually got 2 factors that are the same. So p is equal to 5/2 is an equilibrium. And so this is what we're looking at. 5/2 is the equilibrium. Everything below 5/2 decreases and dies out. Everything above 5/2 just goes down to 5/2. So in essence, this is the maximum 25/4, whatever that is, 6.25. That's the maximum amount of harvesting that you can do and expect the population to continue. If you harvest any more, it's going to die out for sure. If you harvest less, then that's probably better, because this is really tenuous. If you're here at 5/2, like if you just have 1 year that's a little colder and a few of the fish die, then it's like, well, we're going down to extinction. So anyway, on Python, if you want to see what this looks like, here it is. So it's going to look similar, but it's yeah, there it is. Those are those times to extinction. Okay, it's not going to let me. Okay, apparently it won't let me just zoom out a bit, I guess. I probably can get rid of something up here. Yeah, there we go. Okay, so here, if you start off with 0.5 as your population, it's gonna be, I don't know what the units are, but it'll be 0.1 time units till you go extinct. If you have 1 to start off with, if you have 1.5, and then 2, that's doing a little better. And then 2.5, because that's the equilibrium, that's the whole zoo thing, but it's actually not zoo, it's infinity on the complex plane. And then one more, just for fun, we did, you were asked to do number 7, where you were harvesting more than that. If you harvest more than this, then let's see what the numbers look like. Of course, you'll always go extinct. Yeah, there it is. You end up with some arctangents, which makes me happy. But you can see you always go extinct. It doesn't matter how many. In fact, let's just change this to, let's say we start off with 100 fish, or 100 million fish, or whatever. Then you're still going extinct pretty darn quickly. I mean, look at that. It drops off pretty quick. So 1.4 time units. On my iPad, I'll show you what that one looks like. So here's this. Number 7, there are no equilibria, which means you're always going down, and I just drew that. I mean, that's kind of a poor representation, but most of the solutions are going to kind of curl their way downward. They'll get steeper as you get closer to 0, and there will be some place where they're the least steep. I don't know. So that was 5 through 7. So my apologies about that if it was confusing, but I got excited about it because of the harvesting thing, and also now I used Python, which makes me happy as well. So what else do we need to look at from this? That was actually most of it, wasn't it? Was there anything from the earlier numbers? What is it, 1, 2, 3 or something we need to look at? The logistic growth, it would be probably pretty straightforward. Okay, so let's talk about homework. I keep forgetting with my other classes, but let me see how we're doing in here, just a minute. So in differential equations, and this will be a good segue into, I got to show you something on our webpage, but let me just check homework, because my Calc 2 class, they're having trouble with this my new method of uploading. So let's see what we have here. So I'm not going to name names. I'm just curious to see how many. Oh, okay. Not the greatest. We have 13 who have submitted. That was the homework that was due on Monday. Let me check the one that's due today, which technically isn't due until tonight. 6. Okay, so all right, well done. Okay, so if you're having trouble figuring out, this is sort of the transition week where I'm trying to figure out how to do this so that I can make it easy for me, but I also want to make it easy for you. So if you're having trouble with figuring it all out, I can help you. Let me show you. I can do this actually, just a sec, and then I'll show you my. Just a minute. The other thing that I wanted to show you. Okay, good enough. Just a sec. I have to find. Where is this app? Oh, there it is. Okay. And there we go. Okay, so here's my phone. Where am I? Oh, notes. I don't know. Oh, 1508? Okay. So here's my phone. If you have an iPhone, then you have the, whoops, sorry. Here we go. If you have an iPhone, then you have the Notes app automatically built in. And you see now I know if you have an Android, you might not have but you probably have something similar. So on the Notes app, there's a little paperclip on the bottom. So let's say that I have my homework. I can just press that paperclip and it says, oh, look, there's all these things. Scan document, scan a document. And so let's say that this is my homework. Check it out. We'll do this, great. And then that's page 1. And then we'll do this. Oh, wait, just a sec. Okay, let's pretend that that's page 2. So let's say that that's it. So we'll save those 2. Give me a sec. So this is if you have an iPhone. Why is it not? Oh, here we go. Okay, so here is there. Oh, that second one didn't turn out as nicely, but the first one turned out pretty good. So anyway, once you have this, you can save it. Let's see, I can press the little arrow at the top. It's going to take a minute to prepare. It's always takes I don't know, maybe your phone is faster than mine, but you can save it to somewhere like your files, and then you can upload it from your files to Moodle. So this just requires you to go to Moodle and do that. So that's another way if you want to do it that way. If this is too onerous, we'll talk. Okay, so next week, hopefully we can get this working. Also, one other thing I should mention is that if you go to the library and you go to any of the copiers in the library and sign in using your account, you know how like it's got a little screen, you can sign in using your account. You can scan an email to yourself. That's another way to get it. It's looking like it's going to take forever, so I'm going to just give up for now. Cancel that. Oh, I think this is my phone being slow, not so much I think it normally would work. So that's the deal there. So let's regroup, try to get something up there. Everyone, now, once again, I just care that you've done something, that you've tried it, and get your homework done. So try to get something up there for Friday from today's homework. Right now, there's 6 of you that have done it. So 13 of you have yet to do it. So hopefully you can get it up. And if you're having trouble, come see me tomorrow or after class today, and we'll get it done. Okay, I don't have a quiz for you, sadly, because I got excited about the exam that I just had, but I do have this to share with you just in case you need this. So I'm always concerned about making sure that students have what they need to succeed in my classes. And so I'm providing, you probably already know this, I have these various these are my Valentine's cards that I gave to my wife in previous years. You've probably seen these, but this one is one of the early ones. It's kind of cheesy. So there's these various equations. Then I have this double entendre in here, even though each of us, our limits might be 0. When I apply the squeeze theorem to you and me, I find that our limit of our love is unbounded. Lovely. So I've got that. I've got some others. I'll show you where to find these. Yeah, this one's the statistics one. It's kind of, okay, sample of men were asked to rate the amount of love they felt for their wives on a scale. You could change this. I've got it. You can edit this. So you could change it to girlfriends or just special friend, or boyfriend if you're, do a female. But anyway, so there it is. And if you don't love, you could always change it to like, the amount of like. But anyway, open it up. And then we have this, that I was an outlier. So there you go. Very nice. And then, this one, yeah, this is just some sort of a biology thing. So I love the way you fold your proteins. I know that's a little racy, I know, for Envy and you. And then there's, so this one is you and I go together like adenine and thymine. So that's kind of clever, right? And that would be good even if you don't love the person. You can just be like, you're my special friend. You're my best friend. Yeah, that'd be good. So there's that. And then this one, if you don't want to say anything about love other than God loving you, you could have this one. I gave this to a bunch of colleagues a few years ago for Valentine's Day. So it's got the Bible verse about God loving us. And then on the inside, you need more evidence that God loves us. Well, he also gave us mathematics. So isn't that beautiful? You got that little cardioid there. Okay, so that one's got my my brand on it. So if you want to know where, I should also mention this, that in addition to all of those joyous ones, I also have this one. This is our slope field. So on the outside of the card, it says, so you could look up the slope field ones, in spite of the ups and downs, regardless of the initial condition. And then on the inside, it has this. There it is. I love you much more today than the day we met. You can see no matter which solution curve you're on, you're going to be bigger. Okay. Anyway, I know it's kind of hard. I got to explain it to you maybe. I don't know that I need to. You could figure it out yourself. And then, of course, there's this one. You could have all sorts of fun with, that's kind of a cool curve. So you can make your own curves. So there it is. Very nice. So these are all slope fields for these things. Okay, so where are you going to find all this goodness? So what you'll do is you'll go to our Moodle page. Just a minute. So go to our Moodle page under General, and then so it's under General, and then you'll find Valentine's there. So so this is just the past however many years I've been doing this, and I know it looks like a lot, but there's a lot of duplicates here because some of them are PDFs, and so you can edit the ones that are not PDFs. So if you don't like, you can take the slope field and change the words if you don't like my words. So that's the deal there. So you're welcome if you're looking, so I want to make sure that you have what you need to succeed. And that may be, succeed in love, I suppose. Okay, so let's move on. Where did my PowerPoint go? It's here somewhere. Got a little excited. Slope fields, no. Linear models, no. Systems, that's it, systems. There we go. So today we're going to do some systems. So, and in particular, we're going to be focusing on one type of system that's it's pretty easy to explain, but I need to explain what a system is first, and then we'll get to that one type of system that hopefully will be relatively easy to deal with. So if you have two interacting species or two things that react with one another, this is in chemistry, we get this a lot, then a model for the populations or the things that are interacting with one another are going to involve both of those populations. You'll have both, this could be two different chemicals that are reacting with one another. So you have the different concentrations, or maybe here the rabbits and foxes. That's a good example. If you have a closed system like a secluded valley with two different species, the prey and the predator, the rabbits and foxes are a good example. Then the more rabbits there are, the more foxes you could potentially have because the foxes eat the rabbits. But the more foxes you have, the fewer rabbits you're going to have because the foxes are going to eat the rabbits. So you get the picture there. I'll show you this. That'll be actually the last one that we get to. But this gives us a good example of how we're going to write this stuff. So if you have a situation like this, and I'll have several examples that explain this, then you'll be able to say that the rate of change of one population, in fact, we should do the rabbits and foxes first, and we'll save the other stuff for last. So the rate of change of one population is some function of time, the size of that population and the size of the other population, and the same goes here. So in terms of the rabbits and foxes, let me just skip ahead here. Let's see, which one do I want to do? Yeah, let's do this. Or here, yeah, let's see. Will this do? Yeah, this will do it. Okay, yeah, let's do rabbits and foxes. I don't like the way that this is written. I'm just going to write over what I've got. So the rabbits and foxes, R is equal to rabbits, and F is equal to foxes, and T is time. So if you think about it, when you have a rabbit population, dr over dt, rabbits eat grass and carrots and other plant matter, right? So the rabbits don't care about the foxes. The rabbits are happy to live all by themselves without the foxes So without any foxes around, the rabbits are gonna, well, they're gonna reproduce like rabbits, right? And so you end up with this exponential growth. So if there are no foxes, the rabbits are like party time and they just start eating everything and growing their population. However, there are foxes and any fox is going to eat rabbits. And so whenever a fox meets a rabbit, you end up reducing the rabbit population. And so one way to think of this term is anytime there are enough foxes and rabbits around that the foxes happen to bump into a rabbit, the fox is going to eat the rabbit and that will reduce the population. Now this number here, B, is just a number that would express the rate at which the foxes eat the rabbits. So it might be that the foxes eat the rabbits very slowly because they get full and they don't need as many rabbits. And so in that case, the B here might be a very small number, but it still is a number that reduces the overall rabbit population. In the same way, the foxes, you see, foxes are carnivores. And so if you don't have any rabbits around, and we're going to just pretend that there are no other species for the foxes to eat. So if there are no rabbits around for the foxes to eat, then the foxes are going to die out. And they're going to die out pretty quickly, exponential decline or exponential decay. They start starving and they die out. So they need the rabbits. They need the rabbits in order to survive. And so you have this C times F, that's the rate at which the foxes die out. But then we have this benefit that the foxes gain from eating the rabbits. And so we have something like this, that every time a fox eats a rabbit, the rabbits lose, but the foxes gain. And so that's a good example of a system of differential equations where you have two differential equations that interact with one another. We don't have the tools yet to solve this, but we're just sort of exploring these things in chapter 3, and so it's here, so that's what we're doing. Now, let me just show you these are actual data from, oh no, this isn't actual data, sorry. I used to have actual data. I wonder where that went. I'll look for it when we, I thought I actually downloaded some actual data. So in Canada, there's an area of Canada that's pretty isolated where there are hares, that's another word for a rabbit, hares and lynx. Lynx are mountain lions, cougars, yeah. So anyway, they have these two species. What's that? Is that a thing that we're supposed to do? Oh, I do this? Okay, go Cougs. Anyway, yeah, so the lynx eat the rabbits, or the hares. So anyway, I've got the data somewhere from the past 100 years of these two populations. And what you'll find is that the actual data follows this sort of a curve. You have the predators. The predators benefit when there's a lot of prey. So when the prey are at their peak, so if there are a lot of rabbits around, and I'm guessing that these are not the same scale, that there's probably the blue curve is in the millions of rabbits, and the red curve are thousands of foxes, maybe. Just put it like that so that it's a little bit easier to see. But so when you have a lot of prey, the predators are like, it's party time. We're eating these rabbits left and right. But then as they start eating, they're like, whoa, the rabbits are dying off. Wait, where'd all those rabbits go? And then suddenly I'm getting hungry. We're dying off. And so when the prey gets eaten too much, they decline. But then after the foxes start dying, then the prey gain, and you can see this sort of interesting interaction. I'll see if I can find that actual data. I don't know why it's not in this PowerPoint. I know I've had it before. So let's get to a different example, and then we'll come back to the predator-prey if I can find that. So I'll give you something to work on. Okay, so the next thing is mixture. Where do I have? Yeah, mixtures. Mixtures. Okay, so mixture, actually, yeah, let's do the mixtures. So mixtures. So mixing two fluids sometimes gives rise to a linear first-order differential equation. Wait a minute, I just read that slide to you. My apologies. Okay, so here's the idea, is we have something like this. I've got a vat. There we go. Isn't that fun? And I've got, let's see if I can draw this right. There we go. Okay, that's supposed to be like a faucet. Okay, so you got a hose and it's going in there, and then we've got another pipe coming out here. There we go. Okay, okay, so there's some sort of liquid in here. So the easiest way to think of this, I've done this before. I did a presentation years ago on coffee, making lattes. You know, you have coffee and milk and you want to mix it and get the perfect latte. So you could think of this as milk going into a big vat of coffee, and you want to pull your drink off the bottom at the right moment so that it's the perfect mixture for you. But the way that your book has it, most differential equations have it, is the amount of salt in the tank. So we have some amount of salt. This is going to be salt water in the tank. And we need to have some units. So let's just say that there's 100 gallons, just to make it interesting. And then up here, so this is salt water. Maybe we need to start off. So let's do this. S of 0 is equal to 10 pounds. I know. I'm dealing with imperial units here. Sorry. We could do metric, but I think the book has imperial. So 10 pounds. You have 10. So imagine this. I've got this big vat, and I've got 100 gallons of water in there, and I've dumped 10 pounds of salt and stirred it up. Not only that, but you know how the chemistry lab is. We've got a giant magnetic stirring rod down here that's spinning around, keeping everything nicely stirred. So this 100 gallons is always homogeneous, meaning that the salt concentration is the same no matter where you are in the vat. So that's the initial situation. Now here's what's going to happen is I've got these two spigots. So here's one of them, one stopcock. Here we go, there we go. So I've got this one up here and then the one down there. And so this is going to be pure water, distilled water, distilled. So no salt water going into the tank, and it's going into the tank at a rate of 2 gallons per minute. Now you have a similar situation. We're going to be draining the tank at a rate of 2 gallons per minute. So far, so good. You can sort of understand the scenario. What I want to know is how much salt is in the tank after 10 minutes, or after 5 minutes, or even 1 minute. And we can actually solve this without using a system of differential equations. This is just a lead up to the actual system. You see, after we do this one, we're going to go over here and do that one. But that's scary, so let's just do this one first. Okay, so let's go ahead and set this up. I want to know the rate at which the salt is changing with respect to time. Okay, so the rate at which the salt is changing with respect to time is equal to the salt in minus the salt out. Now, first you might say, well, wait, there is no salt going in, and that is true, but I needed to at least mention that because in other problems, in fact, the one that I kind of blinked up on the screen, you're going to have some salt coming into the tank through one of the pipes, and then some salt will leave the tank through this pipe. So you have salt in, salt out. In our case, the salt in is 0 because this is distilled water, no salt going into the tank. How about the salt out? Salt out is equal to what? Well, technically, we're doing 2 gallons per minute. So let's do that. 2 gallons per minute. And this is going to feel a lot like, what is it called? Is it stoichiometry? What is it, the units thing that you learn in chemistry? What? Yeah, stoichiometry? Whatever. Yeah, it sounds fancy. I would just call it unit conversions. I don't know why they have to have a fancy name for it. But anyway, 2 gallons per minute. So I need to know salt, though. This is gallons of liquid. So I need to know how much salt there is in each gallon. All right, well, I could use S. So salt, whoops, let's go back up here and find a different color. I'm going to use S of T to equal the amount of salt at time t. So you have 2 gallons per minute coming out of the tank times S of t is the amount of salt in 100 gallons of liquid. So you see what I just did there? I've got 2 gallons per minute times S, whatever S is, and I know at the beginning it's 10, but it's not going to be 10 for very long. So however much is in the tank divided over 100 gallons, that's the concentration. And check it out, gallons cancel, just like you probably learned back in chemistry class, and you get S over 100 salt per minute. So that's the salt out. What's that? The 2. Thank you. Excellent. Now this is, I mean, you could probably do this in your head, but let me just switch over here really quick and we'll do it right there. So we have ds over dt. The change in salt with respect to time is equal to salt in, there's no salt coming into the tank, minus salt out, 2s over 100. Let me rewrite this one more time, and then you're going to solve it. S over 50. This is easy, separable differential equation, and that'll give me a chance to find my hairs and links. Let's see. No matches? What? Huh. Oh, I found it. That's exciting. All right, I'll show you the hairs and the links in just a minute. This is a Canadian study of the populations of hares and links in, oh, I don't have the exact, it's some location. I'll show you in a minute. Okay, let's go ahead and solve this baby. Super easy, isn't it? Where's my list of people? Oh, come on. Here it is. Okay, randomize. Wait a minute. Sorry, I think I just, okay. Random. All right, Matthew. Matthew, what do you do to solve this thing? You mean like this sort of thing, ds, 1 over s ds is equal to negative 1/50th, something like this? Yeah, so you might have, you could bring the 50 over as well, but I might as well just bring the s, because that's the only thing that matters, right? Okay, let's get our next volunteer. This is pretty easy. Luke, what's next on this solving journey? Ooh. like that, plus C. Oh, wait, sorry, there. Sorry, I got a little ahead of myself. Oh, yeah, okay. Well, I guess that gives us our next step, doesn't it? S is equal to C1 e to the negative 1/50th t. Very nice. So you can solve this, and then of course to get your C, you would use S of 0 is equal to 10 and shove that in here. So let's see, 10 is equal to C1. So that means that S is equal to 10 e to the negative t over 50. Done. So pretty easy to solve this differential equation. Let me show you the hairs and links though, because that's kind of cool. And this I got from some website that I can't remember where. So there it is. So but look, this actual data from 1845 to 1935, and you can see that this is the predator, and so you're following almost the same pattern. You have like the rabbits go up, the predator goes up, the rabbits go down, the predator follows. Then the rabbits are like, hey, we can, we aren't getting killed, and then the predator's like, party time, and then the hares, and yeah, so you have this same thing. Kind of interesting that in nature you actually see this relationship. Probably the fact that it's not as perfect as the differential equation is the fact that in real life you end up with like other things that affect population size, like temperature and other droughts and stuff like that. Okay, so there's that. Well, let's see if we can make things more difficult, because that's what we like to do. Let's see, do I need to keep this? No, I don't. Okay, so we're going to switch to this picture. And so we have two tanks. That's too complicated. This is much better. So I have two tanks. And now these two tanks are connected by a couple of pipes. And, and we actually have to go back. Well, no, we'll do this first. And then we'll go back to the single tank version. So one of the things that you might notice about this, as was the case with the single tank that I showed you, is that my rates of, come on, sorry, it's not cooperating. Let's try one more time. My rates all add up. That is to say, the amount of liquid going into a tank is, let's see, save. Okay, I'll just save this, and then hopefully I can put it in here. Just a minute. So that things are in balance, I guess is what I'm trying to point out. So that looks good. There we go. So the same thing is true here. Everything is in balance in the sense that you have this tank that has, I guess, starts off with 50 gallons of water. And that tank always has 50 gallons of water. The volume in this tank is always 50. And this tank starts out with 50 gallons, and it will stay at 50, because notice that in this tank for B, you have 4 gallons going out of the tank. 1 gallon goes back here, 1 gallon goes here, and 4 gallons going into the tank every minute. So you have things in balance in that sense. It doesn't have to be that way. In fact, I'll show you an example where it's not that way in a minute, but let's do this one where that's nice and balanced. Let's see if we can come up with a model for this. So to do this, and also I should say that to start off, A of 0, we'll use A for the amount of salt in, no, you know what? I just remembered your book does this. X1. So X1 is the salt in this tank, and X2 is the salt in this tank. So X1 is 0, or sorry, X1 of 0 is 25. X2 of 0 is 0, because we're starting with fresh water over here. You'll notice that we're pumping pure water into the tank there, and we're fully mixing. So you've got some sort of a paddle on the inside of these tanks that keeps them nicely mixed. And the mixture gets pumped over to tank B. And then some of the mixture goes back to tank A for whatever reason. And then finally you have this mixture that gets drained off of tank B. So let's see if we can account for everything. So let's do tank A. Tank A I'm going to do dx1 over dt is going to be salt in minus salt out. All right, so look at where the arrows are. You have an arrow going into the tank here, so we have to account for any salt that enters the tank there. Also, this arrow is going in, so those are the in to A, and then you have this one going out. So let's see if we can work this out. So in general, just to make it a little bit easier on you so you don't have to think so hard, the salt in or out is going to equal the rate, the flow rate, times the concentration. So if you think about it, how fast is the fluid? So like here, you have 3 gallons per minute going this direction. That's the flow rate. And then the concentration is amount of salt per gallon. So that's where this, checking the units and everything would come. But it's always going to be this way. So let's do this up here. Maybe I'll just jot these down on the diagram. So here you have 3 gallons per minute, and the concentration is 0 pounds per gallon. Down here, this mixture of 4 gallons per minute is coming out of tank A, and so the concentration of that particular thing is going to be x1 over 50 pounds per gallon. So notice that x1 is the amount of salt in tank A. There are 50 gallons in tank A, and that number of gallons doesn't change because it's always going to be 50. So similarly, you can figure this one out. This is going to be x2 over 50. That's the concentration going out that way. And then this one will be x2 over 50 as well, pounds per gallon. So let's deal with tank A. Tank A, we only have to worry about this and this and that. So let's put it all together. So let's see, salt in. Salt in, you have 0 times 3, or 3 times 0. So dx1 over dt. I know it's kind of silly for me to put the 3 times 0, but that just accounts for this pipe right here. 3 times 0 going in. You have this, that one up there, that's going to be 1 times x2 over 50. And then the salt going out of the tank is down here, 4 times x1 over 50. So 4 times x1 over 50. We'll clean this up in a minute. I just want to get the other tank so that we can have them both up here. So let's do tank. Why don't you go ahead and see if you can do tank B. It'll be dx2 over dt. So go ahead and see if you can put that together. All right, let's see where we are on this. Caden, let's see, we need to worry about 3 things, right? The salt in. Oh, I guess this is the only salt in, isn't it? So Caden, what would that contribute to this particular differential equation? Very nice. So 4 times x1 over 50. Very good. Now we're going to do, that's the only salt in. Now we need to do my salt out. So Zechariah, I guess we have 2 things to deal with. Let's deal with this top pipe first. So what's going to happen with that? Very nice. So 1 times x2 over 50, and then one more pipe to worry about. And Rachel P., what do you get with this last pipe, the one down here in the bottom right? Nice. So we're going to drain that much out. Very good. Okay, so let's clean things up. dx1 over dt is equal to 1/50th x. Oh, sorry. I wanted to do this differently. Let's try again. Negative 4 over 50 x1 plus 1 over 50 x2. And then dx2 over dt is going to equal 4 over 50 x1 minus 4 over 50 x2. Now I've written this in this form, and you should be very suspicious about why I'm doing this. We're not going to do this now, but after spring break, we're going to take a look at this problem again, and we're going to solve it. And can you guess what tool we're going to use to solve this? Anyone going to try? Oh, no, that's too simple. What about linear algebra? Matrix? I know. And here's actually one of the coolest things about this problem is that not only do we get to use linear algebra, but we get to use eigenvalues and eigenvectors. Maybe? No? Yeah, oh, are you in the class right now? Okay, you'll get there. I mean, it was so exciting to me when I learned this because eigenvalue, eigenvectors, they're useless, right? Completely useless until you get to this. And it's like, oh, they're super useful. So I love this for that reason. But for homework, your homework is just going to be like putting together models. This is the model of this particular differential equation. Okay, so let me see. I want to see what else do we need to do on this? Just a minute. So if you bear, seems like I saw something in my homework that I wanted to mention. Here, oh, well, I don't know. Did I make you do that one? Oh, that's easy. You can figure that out. Okay. Yeah, there's one of these. Yeah, one of these is kind of cool because you're mixing a bunch of tanks together. Okay, so let's just talk about one more application. So I wanted to make sure I had all the mixtures. There's one of the mixture problems. You're not only going to make the model, you're going to solve the model, but you'll see it's a little bit simpler than this. You're not mixing as much stuff together. Okay, so the last example of a system comes from radioactive decay. So this is your basic radioactive, this is exponential decay model. If you have a single element, so if you're just worried about one element decaying, that's what you're going to be looking at. But this is not reality. In reality, if you've studied radioactive elements, you find that there's a whole series of elements that one decays into the next, and then that goes into this one, and it kind of branches out. For example, here's the reality of uranium. So if you have uranium-235, here's what the decay series looks like. Uranium, thorium, I think. I don't know. But anyway, notice that it's the same element, just a different version of it, different isotope. And then you have these parallel tracks where it all goes, eventually everything goes down to lead. But each one of these has its own half-life. I mean, look at these, 36 minutes, 2.14 minutes, whatever, bismuth. Oh, I see, they're over here. So protactinium, of course I'd never heard of that, but thorium I have. Radium, we've got that there. Radon, this is, wow, this isotope of radon hardly ever, it's like so fast. 3.96 seconds is the half-life. But anyway, eventually that uranium ends up in lead. But each of these has its own half-life, and so you would have this radioactive decay that you could model with a whole bunch of variables. So 1, 2, however many elements there are, that's how many variables you'd have. We're not going to do that, but we could do 2 or 3 elements in a particular system. So you might have this, that the first element decays into another element at that rate. And then you have, so this would be 3 elements. So let's just call this X, Y, and Z. So X decays into Y, and there's some rate. The lambda is the rate at which it decays. That's not the half-life, it's just the rate. And then the y decays into the z. So, so notice that you're going to have x decays into y at some rate, but then y increases based on how much x there is. So anything that started out as x turns into y, and then y decays into z at some rate. And so the z is going to be based on how much y there is around. So you can see this is a relatively simple version of this really complicated situation. But you could sort of set this up, and actually these sorts of systems are pretty easy to solve. The reason being that you could solve these one at a time. You could solve this because there's only a single variable, x, figure out your solution, and then use that solution here to solve this one, and then work your way down. So those are actually pretty easy to solve. Let's see, do I have an example of this? Oh, I don't. Oh, well. Well, yeah, I get to jump into the mixture. The mixture problems are much more fun. Okay, so the homework is online already. I didn't have a quiz, so that's why we're done a little bit early. I'll make sure I bring a quiz on Friday because I know you're disappointed. Let me stop the recording in case you want